Well, hello. Today, of course, we'll be talking about angle bisectors. But let's take a quick look at what we've done so far. We took a look at midsegments. Remember, we find the midpoint of two sides of a triangle, and then we connect them. And that line is half the length of this line, and it's parallel to this line segment is half the length of this line segment, and it's parallel to this line segment. And that's true if we connect this midsegment to this midsegment, it'll be half of this and parallel to it. We also took a look at perpendicular bisectors. Now we could continue this midsegment and make it into a line, and it is a bisector of this side, but it's not a perpendicular bisector. This is a perpendicular bisector. Remember that from earlier. We have lots of bisectors, but only one perpendicular bisector. So we've got midsegments and perpendicular bisectors. Now we're going to look at angle bisectors. We're just doing this one little piece at a time. I always thought it'd be kind of cool if there was just one big problem we could spend a few weeks on that incorporated all these things we're learning in Chapter 5. But that would be hard to do, I guess. Well, here's some things we'll need to know about angle bisectors. But first, remember we introduced them a long time ago. Long enough that most everyone has probably forgotten it by now. Although the name may give you a clue. What's an angle bisector? Well, it's a line, and it, being a line, it really should have one of those things on it. We could call it a ray in this case. It bisects. In other words, it separates an angle into two congruent angles. This angle is congruent to this angle. That's like the definition of an angle bisector, just as our bisector of a line segment separated it. If we had a bisector here, it separated into two congruent segments. Well, an angle bisector just separates an angle into two congruent angles. Fairly simple. What can we say about angle bisectors? Well, every point on this line is equidistant from the sides which created the angle that it is bisecting. Or, as they say it a little bit shorter, equidistant from the two sides of the angle. These are the sides, and every point on this line is equidistant. That's actually pretty easy to prove. We can do it right here. Or here. Doesn't matter. Let's see here. Remember, the distance from a point to the line is the perpendicular distance. In other words, when you draw a line perpendicular to the original line passing through the point, and the length of that segment from the point to the line along this perpendicular line, that is defined as the distance from a point to a line. So we have a bisector here. We draw a perpendicular line from here to our angle bisector. We can do that. We just construct a perpendicular line. That's legal. This is the right angle. We're not sure what this is, but it's congruent to this one. Also, we have a common side here, which of course is congruent to itself. So, these two triangles here and here must be congruent by angle, angle, side. Remember that theorem? Last chapter. Angle, angle, side. Now, if they're congruent, remember the old CP, CTC, congruent parts of congruent triangles. are congruent. Well, these are the corresponding parts here, which means this side is congruent to this side. But this is in fact the distance from this point to this line. Well, all that proves is that this particular distance from here to here and here to here, these two line segments are congruent, so the distance from here to here and here to here are both equal. What does that say about, say, this point here? What about the distance from here to here and here to here? Well, the important thing to remember is that BD and CD are completely arbitrary. We could have drawn them here. We could have put a perpendicular line in here. We could have put it out here. No matter where we put it, we would still have a right angle here. This side would still be congruent to itself, and these two angles would still be congruent, which means that no matter where we put this, we have two congruent triangles. So this line segment here, which forms one leg in the right triangle we created, is completely arbitrary. We could put it anywhere between the bisector and one side of the angle, all the way out to infinity. It plays the role of a variable in this case. It could be any perpendicular segment from the angle side to the bisector. And since it's totally arbitrary, this congruence must hold for every single perpendicular line we can draw from the side of the angle to the bisector. So it's true from 0 out to infinity. I hope I explained that right. We could put this here, we could put it here, we could put it here. Once we've shown that these two are congruent, we're done, because these two were totally arbitrary. This side and this side, that's not arbitrary. That's given to us. The angle bisector, no, that's not arbitrary. That's given to us. But we draw this in here, we can draw it anywhere. And since we can draw it anywhere, no matter where we draw it, this is going to be true. These two perpendicular lines will be segments, will be congruent. Now, the converse, well, that's pretty simple. I don't think you'll have any trouble remembering that. If you can set things up such that any arbitrary perpendicular line you draw from the side out to the bisector, and same thing over here, if those two are congruent, then we have a bisector. To put it another way, if every point on this line is equidistant from the two sides of the angle, then we have a bisector. Now, this one here, for one thing, you need to remember concurrency means that three or more lines intersect. Similar to confluence, that's where three rivers intersect. If you live in Pennsylvania, you know all about that. Or if you watch football. There's a famous stadium called Three Rivers Stadium, which is built at the confluence of three rivers. Naturally, the sports announcers enjoy saying that every chance they get. Concurrency of angle bisectors. That's kind of a cool word. I may say that a few more times too. We have a concurrency of bisectors here. That means that they all intersect at one point. Anything special about that point? Remember when we had perpendicular bisectors, there was something special about that point that was equidistant from all the vertices. What about the angle bisectors? Now it's funny, I think. The perpendicular bisectors are applied to the sines, and they produce a point that is equidistant from all the vertices, or the apex of the angles. Vertex of the angles, pardon me. Now, if we bisect the angles, we find a point which is equidistant from the sides. Seems symmetric to me. You bisect the sides. Of course, it has to be a perpendicular bisector, and you end up with a point that is equidistant from the vertex of the angles. You bisect the angles, and you end up with a point that is equidistant from the sides. Goes back and forth like that. So what does it mean to be equidistant? Well, for one thing, all these points here would lie on a circle. We can inscribe the circle inside the triangle. This point right here is called the incenter. Remember when we had a circle that included all the vertices, the center of that circle was called the circumcenter. This is called the incenter. So, with these three theorems, let's work some problems. See how things work out with this stuff. Well, here's one that almost looks like we don't have enough information, doesn't it? But what do we have here? Well, let's see. This segment is perpendicular to this. That means that the length of this segment represents the distance from this point to the line. That's the definition of our distance from a point to a line. By the same reasoning, this segment is the distance from the same point to this line, which is the side of the angle. And these two are both congruent. What does that mean? Well, that's the converse of our angle bisector theorem. This line is producing equidistant points, so it must be a bisector. Now, this is a right angle, so we've bisected a right angle. What's half a right angle? Well, I'd say it was 45. You could try a different number and see how it works out. I'd vote for 45. So we've got 3x minus 9. And this will be easy. We just add 9 to each side and get 54. And I think that turns out to be x equals 18. Let's see if that works out. 3 times 18 is 54. Minus 9 is 45. Okay. And 18 was right up here. All we had to do was spot the fact that since this segment is perpendicular, it is by definition a distance from this point to this line. And then remember the converse of the angle bisectors theorem. Not too bad. Well, now we have one of those someone made a mistake problems. What do you think? Would GD be equal to GF? Well, no. These little marks here tell us that we have angle bisectors. Each one of these lines is breaking up the corresponding angle into two congruent angles. That's an angle bisector. And that produces an intersection point which is equidistant from every side. And remember, the distance from a point to a side is the perpendicular distance. These lines aren't perpendicular, so when you say that GD equals GF, you're forgetting the fact that you can't just take the distance from the point to any point on the line. In other words, that's my line. Pretend that's a straight line. And the point, I think I've mentioned before, that's not the distance. That's definitely not the distance. The only one that qualifies as distance is the length of the line segment that is perpendicular and passes through this point. Sometimes it's called the perpendicular distance. But in our case, the perpendicular distance is the only kind of distance that even exists We don't even define any other kind of distance between a point and the line. So if you drew in perpendicular lines perpendicular to the sides here, but passing through this point, now you would have line segments, which were all congruent or of equal length. So this is no good. What about this one over here? He says TV, that would be this segment here. Okay. Is equal to TZ, that's this segment here. Well, these look like, oh I see, they drew the hash marks in. These actually are perpendicular bisectors. And I think I just pointed out in the quick little review, perpendicular, the concurrence, the point at which all the perpendicular bisectors intersect, that is equidistant from the vertices, not from the sides. He just reversed things. These are perpendicular bisectors. They produce a point that is equidistant from the vertices. Also, remember, called the circumcenter. This was called the incenter. So it looks like in this one he just, or she, confused perpendicular bisectors with angle bisectors. If you do that, you'll generate this kind of a mistake. Here we have a diagram. Let's make that a little bit bigger. There we go. That's bigger. Now maybe we should figure out what we can determine from this and see if it matches up with what's down here. For instance, they tell us that this is the incenter. At least I think they tell us, yeah, it says right here, incenter. That means that is not only the point where the angle bisectors intersect, it is also equidistant from the sides. So we can draw in our little congruence hash mark there. These all have to be congruent. What else do we know? Well, we know that these two sides are congruent. How do we know that? Well, just a few minutes ago, we proved that this right triangle and this right triangle were congruent when we draw a perpendicular from here to a point on the angle bisector, and since it is the incenter, we know that this is an angle bisector. And then we draw down the perpendicular from this side to the same point. We have produced two right triangles which are congruent. We proved that a few minutes ago. Well, corresponding parts of congruent triangles are congruent, so those two are congruent. That's a good start. Let's see what we've got up here. NM and NK. Well, there's NM and there's NK. So, looks to me like their congruence is a fact. What about NL and NM? Well, there's NL. Those are both perpendicular distances from the incenter to the sides, so they have to be congruent. In fact, they're marked in right here. I marked them in. What about NG equals NJ? NG, NJ. Well, that would be the same as saying that this point is equidistant from these two vertices. If this is an isosceles triangle, that might be true. Do we know that this is an isosceles triangle? This part here would be. These two right triangles are. But is there any way to know that GM equals JK, and therefore these two sides are congruent? It's not obvious to me, but let's check the next one and see what it says. HK, that's this, is congruent to HM. Well, we definitely could deduce that from the diagram. This is the only one that seems a little shaky to me. If it's true, you really couldn't prove it from the diagram, because we don't have any way of figuring out what these two lengths are here, GM and JK. If they turned out to be congruent, then we would have two congruent sides, and we'd have something more to work with. But we don't have that, so this is the one that we can't definitely say that's true. It looks like it might be true, but there's no way to prove it from the diagram. Well, this one, the idea isn't too complicated, but it's going to use something, at least I think they expect us to use something, that we haven't used through the whole course. It got mentioned back in chapter 1, and then we just forgot about it. It's important, and we're going to study it a whole bunch in a future chapter. But it bothers me to have to use it now since we haven't really studied it very much. What the heck am I talking about? Talking about Pythagoras' theorem. But before we get to that, let's take a look at what we know about this thing here. What would it that would make n the incenter of the triangle? So let's pretend that this is the incenter of the triangle. What would that tell us? Well, these three line segments would all have to be congruent. We know that. We also know from things we did just within the last 20-30 minutes that this side is congruent to this side. In other words, this whole thing, well, forget it, just this side is congruent to this side. So this is 24. Now, Pythagoras' theorem, and if you'd like a reminder, I don't blame you, since we haven't used it in the whole course yet. It seems really odd they would expect you to just suddenly pull that out of your hat. Your instructor may be a lot smarter than me. There may be a way to do this, to find x without using Pythagoras' theorem. Somehow you have to set 14x equal to something, and then solve. And it's not obvious to me how I can use the dimensions I have to set up an equation without using Pythagoras' theorem. So that's what I'm going to do. And if that's not what they expected, your instructor's got a better way to do it. Sorry. So let's try this. Pythagoras' theorem, remember, if we have this is Pythagoras' theorem. We have a right triangle with legs A and B and hypotenuse H. Pythagoras says this. We introduced it way back early in chapter 1, but then we just never talked about it again. You may already be somewhat familiar with it. It's very popular. It almost forms the basis of trigonometry, which we're going to study in a few chapters. I don't like having to use it in this problem. Like I say, I could be making a mistake working it this way. And I'm sure I'll get the right answer, because I know this is a way to do it. It's just that in mathematics, as I said before, there's more than one way to work a problem, and this may not be what they expected us to do. But if we apply this theorem here, this is a leg, and this is hypotenuse. So we could have 14x squared plus 24 squared equals 25 squared. Or I went ahead and wrote some of these out. It's kind of boring sitting here watching me do this in my head. 24 squared is 576, 25 squared is 625, and 14 squared is 196. And of course x squared is x squared. If we subtract 576 from each side, we get that 196 times x squared equals 49. Now, if we divide through by 196, x squared equals 1/4. And what can we square to get 1/4? Yeah, well, it's the funny thing about numbers between 0 and 1. When you square them, they get smaller. So, Even though x squared is 1/4, x is 1/2. So after all that, x is 1/2. And as I say, the only way I see to do this problem, and I guess working in Pythagoras' problem, pardon me, it's not Pythagoras' problem, it's everybody's problem, but it's his theorem that related the legs of a right triangle to the hypotenuse. This is another right triangle. The one we were worried about was this one here. And we had to find this side, or it's called a leg in the case of a right triangle. And this Pythagoras' theorem, well, it's going to come up over and over and over, and maybe even more than that. We'll use it a lot. It's important. So I guess there's nothing wrong with sneaking it in here and there. When we get to it, you will have seen it used once or twice. But personally, I found it an unsatisfying way to do this problem. Here's one. It's kind of interesting, I guess. You got a triangle. Or you may have a triangle. I guess the idea is to figure out which type of triangle would answer these questions. For which one would you need the fewest segments if you're going to produce all the perpendicular and angle bisectors? Which would be produce a pretty messy triangle, right? What is the minimum number of segments you would need? Well, what is the maximum? Perpendicular bisectors, there are 3 sides. We can bisect each side, so there's 3 of those. There are 3 angles in the triangle. We can bisect each of those. So our maximum would be 6, I would say. On the other hand, suppose every perpendicular bisector was also an angle bisector. Well, in a case like that, we'd only have 3 segments, wouldn't we? So for the fewest segments, what kind of triangles are there? Well, with respect to sides, we have scalene, where none of the sides are equal. We have isosceles, where 2 sides are equal. And equilateral, where all the sides are equal. I think it would be sensible, maybe, to look at the 2 extremes of those, the scalene and the equilateral. The one where all the sides are congruent and the one where none of the sides are congruent. Those are the 2 extremes. And see if they correspond to the 2 extremes with respect to the number of perpendicular and angle bisectors. See what happens. Well, I went ahead and drew an equilateral triangle. That was one of our extremes. And when I draw the angle bisectors, and then I draw the perpendicular bisectors, they turn out to be the same line, don't they? Which kind of makes sense. Because if we had an isosceles triangle, I think we already showed that the angle bisector would also be a perpendicular bisector. If not, it's easy to see. The perpendicular bisector and the angle bisector coincide. So we only need 3 line segments to fill this in for an equilateral triangle. In an isosceles triangle, the perpendicular bisector is equidistant from each of the congruent sides. Well, that's also the definition of an angle, not the definition, that is also a property of the angle bisector. So the perpendicular bisector and the angle bisector are both the same line segment in an equilateral triangle. So we minimize with all sides being equal. What about maximizing it? Well, the equilateral triangle is much neater, isn't it? Here we have a scalene triangle. None of the sides are congruent. The blue is the angle bisectors. The red is the perpendicular bisectors. We have an incenter down here and a circumcenter over here. And we had to draw in all 6. None of them coincided. And I expect the isosceles would be right in between the two. Because for an isosceles, one of the angle bisectors would also be a perpendicular bisector. Now that wasn't too bad. Well, that's about it for now.